Well, welcome everyone to the Allen School Colloquium. I'm Professor Jeffrey Hare, and it's my privilege to introduce Shreya Shankar. So Shreya is currently completing her PhD at UC Berkeley, where her research concerns data systems, large language models, and human-computer interaction. Before her PhD, Shreya worked as the first data ML engineer at a startup and her undergraduate degree in CS at Stanford. Her PhD has been supported by an NDSEG fellowship and a Bridgewater Research Fellowship, and her work was recognized by EECS Rising Stars in 2025. In addition to publishing in flagship database venues like VLDB and Sigmod, her work has also appeared in ML venues such as NeurIPS, as well as HCI venues like Chi and WIS, where she's won paper awards. She's also created an industry course on AI evals that has been taken by over 4,000 people at over 500 companies, and her book on this subject will be published later this spring by O'Reilly. And in a social media landscape ripe with both hype and doomerism, I've personally appreciated her balanced, practical, and thoughtful takes on developments in AI. And today she'll be sharing her work and vision on unstructured data analysis. If you have any quick clarification questions, feel free to ask them throughout the talk. Otherwise, wait, and there'll be natural punctuation points to ask additional questions. So with that, please join me in welcoming Shreya Shankar.
Thank you, Jeff. Thank you for the kind introduction. Hi, everyone. My name is Shreya Shankar. I'm a 5th and final year PhD student at UC Berkeley, and I build data systems. So data processing is one of the most ubiquitous applications of computer science. And even if you haven't heard of the term data systems, you've certainly heard of examples like Postgres or Power BI. And there are two what I'll call loops of data processing. There's an inner loop where the system's goal is to take a user's question and get the right answer efficiently. So our research questions here are things like, what languages should users express their questions in, like SQL? How do we plan those queries? How do we store and manage the underlying data? And then in this outer loop, our research goal is to help the user figure out the right question in the first place. So here, research questions are things like, what interactions do we design? How do we design interactions for exploring data? How do we visualize data? And what theories of sense-making and cognition can we draw on to design better tools? Now, research in both of these fields has been enormously impactful. For example, here are just some of the widely used tools out there. So in my PhD, I asked this question, what's next for our field? All of the systems I just showed you primarily operate on structured data, but the vast majority of data in the world is unstructured. Think things like documents, images, video, audio, things that don't typically live in tables. And users can't really use SQL or their favorite data processing framework to do the kinds of operations they'd want to do. So I'll give you an example from one of my users. I work with public defenders in the state of California. Now, California's Racial Justice Act lets defendants challenge their conviction if there's some racial bias in the case. So the data analysis here is quite hard. Right? You have to extract evidence, which is quite fuzzy, evidence of this racial bias, try to do this at scale, try to do this across cases. And in fact, the data analysis is so hard that there's only been a dozen successful challenges in court, not because bias doesn't exist, but because people cannot do this data analysis themselves. Now, use cases like the previous one are everywhere. I've worked with users in medicine and real estate and e-commerce and more. And the challenges of these workloads are quite interdisciplinary. So they're multi-step. They need to run at scale, requiring us to wear a database hat. But these tasks aren't really amenable to precise specifications, like racial bias. What does that mean? Requiring an AI approach. And these concepts are very sociological sometimes, are human defined. They evolve over time, which opens up some HCI challenges for us. Now, I'm not the first person to come here and say we should do unstructured data processing. It's been a pipe dream in our system, or in our field for a very long time. But I'll argue today we can finally achieve it. We have large language models as a new building block to help us. So a few of us in the database community are developing this new subfield of LLM-powered data processing. Is it a real thing? Why should you care? Well, beyond the real and high-stakes deployments from my users, like journalists, climate scientists, and public defenders, many major database vendors are supporting LLM-powered data processing, struggling to keep up with demand. And the research community is really growing. In fact, today, close to 8% of archived cs.db papers are about this topic. So the big research question I want to pose today is, how are we going to take these existing systems and re-architect them for LLM-powered data transformations. Now, my research actually develops both of these two loops. Here's my approach to doing research. I build data systems for emerging paradigms. Today, that is unstructured data processing. And I deploy my systems wide or open source and deep or in year-long collaborations. I like to work with folks and applications in different areas. And what I learn from all these applications develops better system internals for that inner loop, as well as user-facing interfaces and understanding of user behavior for the outer loop. And this is a flywheel approach. It's allowed me to have a lot of impact in my PhD. I built an open source system that's gotten some traction, led to many long-term collaborations. And our query optimization techniques have have been integrated in databases like Snowflake and BigQuery. Our work in interfaces has inspired the interfaces of major AI systems like LangChain, ChromaDB, and OpenAI. And our theories of user behavior have been cited by practitioners and academics alike. We have the most cited paper at WIS24, as well as the second most cited paper at CSEW24. So with that all out of the way, today I'm going to talk about DocETL, a system I built in my PhD. I'll tell you a little bit about what we did in this inner loop, specifically in query optimization in DocETL. Then I'll tell you about some of our work in the outer loop, specifically tools for people to iterate on queries. And finally, I will conclude with some ideas for future work. First, I'll better describe the public defender's workload to ground the examples in this talk. Then I'll give an example of a DocETL query so you can see the syntax. So public defenders, as I've mentioned before, doing this really hard data analysis task, they receive bulk discovery dumps containing thousands of different docs, so court transcripts, police reports, rap sheets or history, spanning multiple defendants and cases, and they want to run hundreds of queries across these defendants and cases. The more queries they run, the better argument they can prepare. So what are these types of queries? Well, there's several different types of operations. There's extraction of bias, language, and facts from each case. There's some sort of synthesis or summary generation. And there's also comparison across different cases with similar facts. So all of these are fuzzy operations, as I'll show you examples of, and they need LLMs to help. And I know it sounds weird to kind of operationalize AI in this way, but I assure you public defenders find this useful. Even if it's not perfectly accurate, they can learn from some of the results and speed up their analysis. Now, if we try to automate these kinds of tasks naively by, say, stuffing everything into a large language model, all of these operations, all of this data, it's not going to fit. It's not going to be accurate, but assume it could, it's still going to be prohibitively expensive. So a system like DocETL needs to deliver both high accuracy as well as low cost. Now here's one example DocETL query out of many. This contains two operators. It's very simplified to be accessible. And each operator works over documents, which are collections of key value pairs. I'll show it like a table. Here we have trial transcripts, each with ID and transcript keys. And the map operator takes a prompt, which is determine the judge's name, and an output schema for the new attributes that's going to produce. Magically, this operation will run, creating the new attribute. And the reduce operator groups by the name and summarizes the common implicit biases across these trial transcripts. Okay, so this prompt is applied to all documents of that judge's name. And the output schema is very similar, and the result will be this set of documents with name and common biases attributes. So note that DocETL here is a declarative system. Users specify what they want at a high level. They're not specifying how these operations are going to run under the hood. These are map and reduce operators. And in the beginning, actually, we had 4 such natural language operators, also including filter and join. But we had to add new operators later, as I'm going to discuss. And these are relational operators, these are inspired by relational operators. But 2 things I want to point out here. First, in our setting, there's no formal or mathematical notion of a correct answer anymore. Right? Something like summarize the biases of a judge doesn't have one right output. Correctness instead has to be evaluated empirically. This is going to be very uncomfortable from a database perspective, but it's going to also have big implications for how we think about query optimization. And then second point, some of you may be thinking, can users even express such queries? Do they have a precise definition of implicit bias in their head? Hold on to that thought. I will come back to it in the outer loop. Okay? So now let's talk about query optimization, which is basically how do we take that user's query and turn it into a good execution plan that meets accuracy and doesn't break the bank. Now, I've organized this part of the talk by components of a traditional query optimizer. First, the space of query plans, which defines different ways to execute a query. And second, search. How do we find the best or lowest cost plan? So for each of these, I will start with background how we solve it in traditional databases, then what is new for unstructured data, and then our solution in DocETL. So let's start with this plan space. Now, databases typically use rewrite rules to produce logically equivalent but more performant query plans. So what are these rewrite rules? Some are algebraic, like projection or filter pushdown. Intuitively, they reduce intermediate data sizes. So an example for filter pushdown, say we have a SQL query that looks like this. We're joining two tables. There is a filter. We can push down this filter to be closer to the source table, reducing the number of rows that need to be joined, thereby making the query plan more efficient. Now, other rewrite rules concern the implementation of an operator. For example, maybe for this yellow, this join node, since it's an equijoin, we can execute it with a hash join algorithm instead of a nested loop join. Okay, so there are actually hundreds, maybe even thousands of rewrite rules in modern query optimizers. This rewrite rule framework has served us very well over the decades. So I thought it was quite natural to build DocETL this way. All the algebraic rewrites apply to DocETL as is, and we can have field day coming up with lots of different implementations for these natural language operators. We can vary the large language model. We can vary prompting strategies. We can ensemble models, do all of these things. And forget search for a moment. What we found was that if we exhaustively enumerate all plans, none of them are good enough for real users. So here are some results for a query. The details are not relevant, but plans end up being too expensive and too inaccurate. And what we really want is query plans in that upper right quadrant, cheap as well as high accuracy. So we wondered, yes?
Sorry, you said that you exhaustively enumerate all plans, but then there can't be a plan in the red box.
We did using some rewrite rules that we defined, which are changing model, changing prompt, using like a retrieval augmented generation strategy, searching. And that is a pretty good space of various different algorithms that you could do. What I'll show you in a bit is how we will get to a better plan. Yeah. So we wondered, how do we solve the problem? It turns out LLM accuracy varies, not just based on how hard the task is in the prompt, but also based on data characteristics. On the right is an example of a single operator query. Find all statements that indicate implicit bias running on many long documents. Now, to that first bullet point, LLM accuracy decreases for the same task if the document is longer. And then second, if there are more facts to extract, like more statements of racial bias, the accuracy decreases. So to solve this problem, one might decompose the tasks. What do I mean by that? We could maybe decompose those documents into smaller chunks. We could maybe decompose the prompt into two different prompts. And really, people explore these decompositions manually. They do it outside of the data system, which requires a lot of toil. And the million-dollar question that we really had was, can we automatically express these kinds of decompositions in the rewrite rule framework so the database can search over them? This would be huge, but it turns out to be pretty hard, because if you think about it, decompositions aren't necessarily logically equivalent to the original query, only semantically equivalent, which is loosely defined, not even defined. And the rewrite rule framework was only designed for these logically equivalent rules. So we have to adapt the rewrite rule framework to move to this new concept of semantic equivalence. We call our solution rewrite directives. Now, directives instantiate new operators tailored to LLM capabilities. They are abstract. That's why we call them directives. They're instantiated by reasoning about the specific data and the task. So here's an example for data decomposition. It looks like a rewrite rule. But some new things are we first had to add new operators to do DocETL to enable them. Second, LLM agents instantiate them. There can be infinitely many such. And third, many of them might be bad. We have no way of knowing if they're semantic equivalence is not well defined. So we had to measure accuracy on samples, and this is going to make search tough as well. So let me show you some pictorial examples. Here's a rewrite directive for data decomposition. Imagine you have a map operator to extract all statements indicating bias on a long document. We can rewrite it as first splitting this document into chunks, running the LLM over each chunk. This improves the per chunk recall. and then repurposing our existing reduce operator to do an entirely different task, which is combine or deduplicate the statements of implicit bias. Okay, so the output of this better matches the user's original intention, still meets the same output schema constraints. Now, similarly, we can also express prompt decomposition. Maybe implicit bias can be decomposed because there's many different types of implicit bias. So we might rewrite this plan into one that has a different map operation for each type, improving the overall accuracy. Now, these are just two examples, just to give you the intuition. I also mentioned we needed new operators. I'll motivate two such new operators, one data-oriented, one prompt-oriented. So this gather operator, it's data-oriented. The motivation is as follows. If you split a document into chunks, it turns out many chunks do not make sense in isolation. How do we solve this problem so the LLM can do the map operation? The gather augments each chunk with the relevant, what we call peripheral context needed to make sense of it. So gather is very flexible. There are many different peripheral configurations. For example, you could have a sliding window of previous or next chunks. You could also imagine having a summary of all the previous chunks being fed in. And also for a lot of documents with tables of contents or some header hierarchies, that also can be used as peripheral context. So there are many such of these gather configurations. Then this resolve operator assists in task decomposition. So why do we need it? Here's the same MapReduce pipeline I had earlier. Turns out if you want to do a reduce or a group by on an attribute generated by a DocETL map, the map might inconsistently extract attributes. So concretely, if we have these many documents and we want to group by the judge extracted, they might be extracted inconsistently, and therefore these judges that are supposed to be in the same group won't be. So our solution to this is to insert a resolve operator before every reduce. Resolve just elevates entity resolution to be a first-class operator, and we can optimize it using blocking techniques drawn from the database community. Now, of course, another idea is we can improve accuracy. We have new operators to do this, but we could also use rewrite directives to improve the cost. Maybe we can do the opposite what we did before, fuse together into one operator. Or we can replace operators with code. Again, the details are not relevant, but these are things that can reduce the cost while hopefully maintaining the same accuracy. Yes?
You showed a bunch of different prompts, like we take this prompt and we break it into other prompts.
Yes.
But presumably the way it's broken into other prompts depends on what the prompt is. So
Exactly.
If I wrote down a rewrite rule, I don't understand how that would know how to transform a prompt.
Lovely question. We use LLM agents to do this. So we break down this map operator into many different map operators depending on the semantics in this prompt. And the LLM agent can come up with these. And we also make sure that there's typing checks to make sure the overall plan makes sense.
And, sorry, just follow up
Yeah.
on that. So that means then if you run plan again, there's no reason you would get the same query, like that's unstable to the planning process.
Sorry, I don't think I followed.
It's not just that the plan with its prompts can produce different results if you run it
Right.
multiple times.
Right.
The process of coming up with the plan
Yes, yes.
also produces different plans non-deterministically.
Yes, exactly. So in our optimizer, we just enumerate different, like 2 or 3 different instantiations. You could have many of them. This makes for an interesting search problem, for sure. Yeah. All right, so bubbling up, turns out we have 15 operators and 31 rewrite directives in DocETL's query optimizer. You can check them out in our latest paper. But we also include rewrites drawn from LLM research, things like prompt optimization and self-refinement. The idea here, or a thesis, is that we need to be an extensible framework to admit different rewrite ideas as they come from different communities. So to recap, we talked about this plan space. We motivated the need for these new semantic rewrites. Rewrite directives are our solution in DocETL. Now I want to give you a sense for what it means to search over this space of rewrites. So how do we do this in traditional databases? Well, traditional databases typically optimize for a single objective, latency, and there's a single best plan to return. In DocETL, what's different is that we're optimizing for multiple objectives, and we also return a Pareto frontier of plans so the user can pick the trade-off. And then for the actual search algorithm itself, query optimizers typically use dynamic programming, like in Selinger's algorithm, or memoization, like in Volcano or Cascades. But this relies on the principle of optimal substructure, that you can break the best plan of an expression into the best plan for its sub-expressions. Now, unfortunately, optimal substructure doesn't hold in this LLM case. Why not consider a map-reduce pipeline? You think all we want to do is vary the choice of the large language model. Okay? The best LLM for maybe a map step or an extraction step actually depends on which LLM is doing the summarization, because the behaviors of these models may not be cleanly composed. Right? They might have their own biases. These models may have their own biases. Sorry. So we realized, OK, we've seen this across many different applications. We probably need to come up with a new search algorithm. But first, we tackled a simpler version of search, even searching in one direction, cost, not accuracy. And for a simple map or filter operator pipeline, this turns out to be difficult. So how do we do it? I'll illustrate via an example. Say we have this filter asking whether the judge makes racially biased remarks at sentencing, running on full documents with GPT-4o. So what we want to do is make this cheaper while maintaining the accuracy of this plan. So what can we do to make it cheaper? We can send in less data to the LLM, maybe just the top K chunks. We could also try to use a cheaper model, say a mini model instead of the 4o. Or third, a la rewrite directives, the operation itself can change. So maybe in this case, we could have it be a simpler prerequisite for the original operation. Like the transcript has to have a sentencing hearing in order for there to be racially biased remarks at sentencing. So this is a much cheaper plan. But the problem is it definitely doesn't match the accuracy of the original. How we can restore the accuracy is say, if this operator says no with high confidence, predict no for the document. Otherwise, fall back to the original operation. So all the thought about how we get the confidences. There are many ways. I'll tell you what we do later. But we call this architecture a task cascade. So this is the same as the previous slide. I just abstracted the operation, gave a little bit more compact notation. How we make sure the plan meets the accuracy target is by tuning the confidence threshold down. Now, our goal is to make this as efficient as possible. The Sankey diagram is a better way to visualize efficiency. The width represents the number of documents an operator sees. And you can see that all the documents go to that first operator. Some exit in green, the confidence ones. Some hit the expensive original in gray. Our goal is to minimize the gray. And we can do this by chaining multiple tasks together in the abstract, each peeling off more documents before they reach the original. So the cost model for such a task cascade is to pay per token with caching discounts, often a lot of caching discounts. And there are multiple challenges we face in constructing one of these cascades. I won't have time to cover the first two, task generation and selection, but briefly, we show that a simplified version of this min-cost task ordering problem is NP-hard, and we use LLM agents to help suggest tasks and pick subsets of these tasks that cover as many documents as possible. But now for this third, which is setting thresholds to meet accuracy targets with respect to the original, this problem gave us the most grief. How the approach works is to label a sample with the original plan, search over candidate thresholds, and pick the lowest threshold that meets the target accuracy on the sample. And typically, we want a statistical guarantee that the accuracy is met on the full data set, not just a sample. A standard approach to get the statistical guarantee would be to use concentration inequalities, like Hefting's inequality, to bound how far sample accuracy is from the true accuracy per task. Then use a union bound across tasks so the guarantee holds for all tasks simultaneously. The problem is that task cascades can have many, many tasks to be efficient. So the union bound gets loose, and we would need many samples in order to get these accuracy guarantees. So in our paper, we also propose a new threshold finding algorithm to test. And the ways that we reduce the number of samples are first, test end-to-end cascade accuracy directly, avoiding the union bound. And then second, we also use newer bounds from the statistics literature. These exploit low variance. And if you're interested in those details, please chat with me on the one-on-one or read the paper. But more importantly, this cost reduction is very good. Across many different workloads, at 90% target accuracy, we found plans that ended up being 86% cheaper than the original operator. And if you compare to just varying the model, so you take out our rewrites around changing the prompt, changing the data, those model cascades are, we are 49% cheaper than them. Yes?
Clarifying question. Does 86% cheaper mean $1 goes, like it only cost me 14 cents I'm trying to understand what that
Yeah, what the scale is
yeah,
of these.
What does, yeah, I don't understand.
It's a great question. People spend thousands of dollars on these queries to run like tens of thousands of documents. Each of them could be hundreds of pages. So cutting the cost that much can be a lot.
Okay, but 86% reduction does mean if I've spent $1, now I spend 14 cents.
Yes, yes. Great. So you can see there's a lot of depth even in that simpler setting of rewriting a single operator query. But that's not enough. We have to rewrite for cost as well as accuracy. And I won't go into detail on how we do search for cost and accuracy, but we use Monte Carlo tree search to do this, to learn the best rewrite sequences for a pipeline. Nodes are pipelines, end-to-end pipelines. Edges are our rewrites. The upper confidence bound algorithm picks which pipeline to rewrite based on how much it contributes to that Pareto frontier of cost and accuracy. LLM agents generate the rewrites. And then our ground truth here isn't this nice Oracle LLM anymore. It is user-labeled samples, a user-defined accuracy function. And here's an example. Here's a slice of the search tree for optimizing one of the public defender's workloads. We're able to cut 95% of the cost and 1.5x the accuracy. So the user started out with something pretty abysmal, 47%. It's actually, recall it, precision 90, but and then they got to something much better. And I also include the red rectangle on the left, which is 22% worst accuracy pipeline. So you can see really how high variance these accuracies are. It's really important to pick the best plan. We also compared to other baseline systems across open source workloads. So one set of baselines is open source unstructured data processing system. So think of these, none of these use rewrite directives. Another baseline is, okay, what if you use a state-of-the-art LLM agent to author whatever pipeline it wants, allowing it to use DocETL query engine, run it on samples, observe, ablation of our structured search algorithm. All of these systems can search across many different models. And we find plans that are up to 3.1x more accuracy at 46 to 56% lower costs, which is really exciting. What are these plans that we are finding? They're 2 to 3 times more operators than the baseline pipelines. 9 different rewrite directives are used to get these top accuracy pipelines, underscoring you need a diversity of rewrite directives. And over half of the top 5 accuracy plans include some agent-synthesized code. So here's an example. For a medical task, details of the task are not relevant. But the agent synthesized this complicated regular expression that I certainly would not have been able to come up with. And it ended up dropping 75% of the document while maintaining the same accuracy. And more such of these examples are in our paper. But with that, what's the key insight that I want to tell you from this query optimization? It's that unstructured data queries can be rewritten semantically. We can change the prompt. We can change the data. We should do this in the database. We formalize the idea with rewrite directives, and searching over them is quite hard. Yes?
Maybe I missed it. How do you determine accuracy?
Users label a sample and provide their own accuracy function. So that could be accuracy, F1, precision, recall.
So, for instance, if you're doing a bunch of different plans, they need to do that for each plan.
Right. We have to execute those plans on samples to measure the accuracy and cost. And that makes it slow. We don't have that many pipelines we can search over. It really makes the search problem hard. Yeah. I'll take one more question. Yeah.
So they're labeling data before it goes through the plan, right?
Yes, most of them do that. Well, let's talk later. Yeah.
Yeah.
Great. All right. So with that, I want to move to some of the outer loop portion of my work. I'll mainly talk about my DocWrangler project here, which studies how users should author unstructured data queries. And so remember this example pipeline from earlier. I mentioned these prompts are very simplistic. We assumed the user could come up with good prompts, which in practice is not really true. Users, why is this hard, right? They have to translate their domain concepts into some language that LLM understands. And moreover, for many concepts, there's not even a one true definition of it, right? Something like implicit bias. So with DocETL and systems of the like, users have no way to explore the data and iterate. So the big research question I had was, what tools do users need to effectively trust and steer unstructured data analysis? So I built DocWrangler, a mixed initiative integrated development environment for writing DocETL pipelines. There are 3 contributions of this work. The first is a framework for understanding user-facing challenges in this new DocETL paradigm. The second is UI components for each gulf of challenges that combine direct manipulation with LLM assistance. And third, this is what I'm most excited about. Because DocWrangler is really the first IDE out there for unstructured data analysis with LLMs, we had a unique opportunity to use it as a design probe. We ran both lab studies and an online deployment to uncover new needs and patterns. So before I go through these contributions, I kind of want you to feel the vibes of DocWrangler. Don't worry about following the user journey. I know it's going way too fast. I'll step through some features more slowly later. But I want you to see that this is a full-fledged IDE that people spend hours and actually days based on our data really working. All right, there's so many different features. How did we design this? We started off by building a theory of what makes DocETL pipelines hard to work with. Okay, so we released it open source. We talked to our users. I analyzed lots of messages from GitHub and Discord, did a bunch of contextual inquiry with DocETL. And what I found was that all of these user-facing issues could be categorized into 3 gulfs. Gulfs between the user, the data, and the pipeline they're writing. So the term gulf here is inspired by Norman's gulfs for UI development, but it's a refinement for data processing as well as LLMs. But I'll explain it to you. The first gulf users have to cross is this gulf of comprehension, which is that users have no idea what is in their data. They have trouble understanding it, especially all of the output, the unstructured data that LLMs produce. Okay, what makes the problem also hard is that unstructured text at this scale is not really amenable to visualizations. Visualizations and summary statistics being the tool that we had for the structured data world to help comprehend data at scale. Now, the second gulf is this gulf of specification. So the user knows what's in their data. They have an idea of what they want to query, but they can't express it in DocETL. And then this third gulf, this entirely new gulf, is even if they've figured out how to specify it well, this LLM pipeline may not work. It might not work, be accurate on all of the data in their data set. Right? So we can't assume a well-specified will always work. This gulf has to do with LLM capabilities. Now, these 3 gulfs correspond to distinct categories of challenges, like 3 different hats users have to wear when authoring pipelines. So we needed to design different tools for each gulf. I'll walk you through one UI component we built for each gulf. To illustrate how DocWrangler supports the 3 gulfs, imagine you're a medical analyst. This is one of our users. You're trying to extract medications from transcripts of conversations between doctors and patients. Okay, so your task is to extract medications mentioned. You'll start out by opening DocWrangler. You'll write some prompt. The details of the prompt don't matter. It's pretty basic. And the first challenge you'll run into is just figuring out what it is you even want. Right? What is the long tail of LLM behaviors? How does that relate to my task? How we solve the problem is to A, visualize all of the outputs based on their types. So for structured outputs, that's quite useful. And then B, we have a viewer that allows users to inspect documents row by row. So here, they can see the LLM output on the left. They can see the source on the right. Maybe they line up the output with the source data. And then pretty much all the time, the users see something, like these dosages here, and they think, oh, that's important. I actually want that extracted as well. So users then can add that as a note, and they can forget about this and continue reviewing their outputs. Maybe sometimes they see things that they don't want. So maybe they don't want over-the-counter drugs included in their analysis. Again, flagged as a note. So all of these reflections, these notes accumulate in this notes panel on the left. In practice in our studies and in the online deployment, people will make up 20 to 25 notes before moving forward. And this doesn't just help people kind of crystallize their thoughts. These notes also carry forward to the next 2 gulfs. Right? So this gulf of specification next. The challenge here is once you've written them down, how do you actually turn these into better specifications or prompts for the LLM? With DocWrangler, you can click Improve Prompt for any operation anytime. And DocWrangler will turn your notes into an improved prompt. So it shows you the rewrite as a diff. Users can interactively edit it or ask DocWrangler to edit it indirectly. And this saves a lot of time, we've noticed, in specification. Now, people go through multiple rounds of this, providing notes, improving specification. And at some point, these operators get complex enough. Maybe they've realized they want 3 things extracted. And they don't always work accurately at scale. So maybe here the user has realized that this primary complaint they wanted extracted is not actually correct. How do we solve the problem? Well, we are constantly running DocETL's accuracy improving rewrite directives in the background. If we notice that there's something that could be more accurate, then we give them a notification, we propose a new pipeline, and then they can run it on their data and then see that it performs better, replace it if they would like, otherwise go back to the previous. So those are just 3 different features we implement. We also implement more like provenance, ability to show intermediates. And there were some technical challenges like dealing with context management and memory. But I won't talk about those technical challenges. I'd rather tell you about the cool things that we learned in our evaluation. We did in-person think aloud studies with 10 participants. Many of them brought their own data sets, as well as an online deployment where users brought their own API keys. And we collected data to this day from 4,500 pipelines, 1/3 of which we analyzed for our WIST paper. This has over 30 gigabytes of underlying text documents. So that's 5 billion words people want to make sense of. And we did a both quantitative and qualitative analysis on all of this data. And what did we learn? I'll tell you 4 key things we learned. First, users iterate a lot. Okay, they iterate between writing operations, inspecting data and outputs, and improving operations between 10 and 20 times. So clearly, DocETL queries are not simply something that you can kind of one-shot your way to the answer. Second, people didn't want to read raw documents, even though we built features to make it easy, like document inspection and search and filtering. And one would think, right, reading data is necessary to write a good prompt. For example, a user might want to find transcripts where the patient trusts or distrusts a doctor, but this is a terrible prompt. They need to understand what trust might look like in order to have a better specification. What would they do instead of reading the documents? Well, they would create a new exploratory map operation to summarize the document in this task-specific way, read these summaries to then inform what to put in their other operator prompt. And in fact, in about 1 in 5 pipeline edits, users were adding and removing these pipeline operations. So it's a lot of iteration. So users avoid reading the documents when writing operations. But surely, when they're checking the LLMs, the outputs, they must go back to the source, right? Not quite. To validate LLM behavior, users instead like to add a reasoning attribute to all of these DocETL operators. And even though it might take longer to run these operations because now the reasoning has to be generated, they were OK with that because now with the outputs, they could simply read that reasoning attribute and try to avoid reading the source document. So 2 participants in our study independently discovered this strategy. And really, this taught us a lot about exploratory actions, which spark ideas for future work, of course. Exploratory operators should not be optimized as intensely as our analysis operators. And even the interface could offer lighter weight ways to explore. Rather than make the user write prompts, maybe we can show them better interfaces like highlight hot regions in documents, support some form of query by example. But anyways, to our 3rd point, interestingly, underspecification is a feature and not a bug. Like users intentionally underspecify. So for example, I'm bringing back the same query where the prompt is very underspecified, just true or false for trust or distrust. After looking at the histogram in the first column, a lot of them are false. The user reads the rationale why. And instead of trying to put in a high effort way to improve the prompt, they simply edit some of these output schemas. Instead of being binary, true or false, they make it low, medium, high, and then rerun the operation, again, without having read the data, thought about the prompt. And then they can scroll to that visualization of that new attribute and sanity check whether that histogram of low, medium, high aligns with their expectations. Right, so I thought this was super interesting. People really coupling the visualizations here with their underspecification, intentionally doing that so they could quickly get to a better output. A funny term that one of our study participants gave to this behavior is prompt rubber ducking, this idea of intentionally asking vague questions and refining them over time. But in all of this rapid iteration, I think the biggest theme that emerged is that users really need to slow down. It's so easy to move fast, much faster than their cognition can keep up. And interestingly, in our online deployment, over half of the automated prompt improvement usages had 0 user notes. Okay, so that means in many cases, users already ran the pipeline. They had sample outputs available. They didn't look at them. They clicked improve prompt, hoping that DocWrangler will read those outputs and improve the prompt. Okay, so we've painstakingly built this human-in-the-loop interface, only to find that humans are taking themselves out of the loop, which is a little bit concerning, right? So jokes aside, I think my bigger lesson here is that it's way too easy to let the LLM think for you as a user. And as a system designer in the Gen AI world today, my job is to put the friction in the right places. So some of our features in DocWrangler, to your question in a bit.
Sorry, whenever you're done.
Yeah. Some of our features unintentionally created good friction. For example, one of our participants, every time he reached the output schema in DocWrangler, he noticed he had to stop, think about what the types would be, think about how that output fit in the context of the broader pipeline, and he called these moments of reflection speed breaks. And I think that's an apt term for what we want to be building. There are a couple of questions here. Sure.
Before you said that the optimization on queries works by having labeled data for determining accuracy.
Yes.
It seems like the labeled data has disappeared.
Here, users can provide labeled data. It doesn't work nobody comes with it. We use LLMs as judges in the background, implementation details, and use the LLM judge to see if the rewritten pipeline output would be higher quality than the original pipeline output. Happy to talk about those technical details offline. Yes?
So is the critical piece about the human in the loop. So what's the latency and how does that scale with the number of documents inputted into the system?
Good question. I haven't seen people use more than like 10,000 documents in this system. And the latency can be anywhere from like 5 seconds to like, I've seen 30 minutes for this 10,000 document use case. The latency for the AI-assisted features like prompt improvements, that's much better.
Then updating UI in real time, if let's say the query is taking like 30 minutes, are you providing those histograms as the documents are being processed? Or is this keep the tab open and now I'm doing another task in a different place?
Great question. We are not updating the histograms real time. That is something that is definitely we should do. Yeah. All right, I'm going to move on. We can get to more questions later. Plenty more of such insights can be found in our paper. And really, we were able to get the many rich insights thanks to our online deployment users. Here's just a sample of them. And really, this project reinforced for me that co-developing that inner and outer loop can drive adoption. People have joined our communities. People have made YouTube videos about DocWrangler and written blog posts, which is very exciting. So the one big takeaway from DocWrangler's work is that we have these 3 gulfs of user challenges, and we definitely can build lots of tools to help people with them. Last but not least, I have one slide I want to briefly touch on, a generalization challenge, evaluating LLM outputs at scale. This problem is very interesting to me because it's very hard and human-centered and applicable beyond data processing. I've written a few papers on this problem. The general class of solution is how to design better automated evaluators. So here are some of the key insights we found. One, you can take the exhaust users generate in an interface, like these prompt deltas, and figure out how to turn those automatically into evaluation criteria. So here, maybe in the summarization task, based on the diffs in the prompt, the user clearly doesn't want sensitive information included in the output. So you can turn that into a guardrail automatically. We formalized this prompt criteria mining problem and selection problem, build a system around it. We deployed that with a startup called LangChain, collected a bunch of prompts and user evals from it, and also open sourced that. Other ideas that we've explored are applying interactive machine learning ideas now to this LLM setting, collecting labels as users are anyways waiting for outputs. And user studies of this work has found that as users label more outputs, their own rubrics, their own criteria really changes what we call criteria drift. It drifts with more and more outputs. And the idea of really using the interface to improve LLM evals and alignment got traction, several large tech companies. And for fun, over last summer, I created a course on AI evals along with my industry friend. I designed the curriculum. It was very successful. This process that we designed is verbatim adopted by OpenAI and their forward deployed engineering team. And the course reader that I wrote is also being published by O'Reilly in a couple of months. So this concludes the research portion of my talk. In the last couple of minutes, what's next? What's next for the research agenda? So today, I think we are just at the cusp of unstructured data analysis. I built tools in both the inner and outer loop for unstructured data processing, and some of these ideas have resonated more broadly. But as a faculty, my goal is to really make unstructured data processing ubiquitous, ideally like structured data analysis. There are 3 research thrusts I want to pursue. One, going deep in the stack, building the best system possible for unstructured data analysis. 2, going wide in the life cycle, the full life cycle for unstructured data. And then while I study these loops, I'm also broadly interested in how AI is changing knowledge work, and I want to study these problems. I'll briefly talk about each of these. So going deep in the database stack. So here's canonical layers of a database stack. I've done research at the top 2 layers, and even here I think there's opportunities for future research. For example, in that operator layer, sometimes natural language is not precise enough, especially for an operator like a filter. Perhaps we can explore something between natural language and maybe more precise code. In the query optimizer, LLM agents take a really long time to do these query rewrites. I want to train something faster, heuristics, maybe RL agents. And then in these bottom layers we've not really visited, I think there's lots of opportunities around using open source LLMs, custom KV caching for our kinds of workloads, and at that storage layer, thinking about new indexes for DocETL filter and joins. We also have a rank operator, so not ranking by natural language, thinking about the indexes we want to do there. Then the second thrust I want to pursue is going very broad in the life cycle. So far, I've built systems for authoring and executing queries, but there's these bookends, right? In the beginning, how do you even know what questions are worth asking in your data? What does that document discovery look like? I'm interested in formalizing those more exploratory operators we observed in DocWrangler, turning that into a better interface. And then after you get results, you need to kind of explore them and share them with collaborators. And I'm interested in this idea of building the business intelligence equivalent, but for unstructured data. And I'm also interested in revisiting ideas about collaboration and collaborative visualization here. And these are the system artifacts I'm imagining, but in this thrust, I'm also very intellectually interested in what principles, what new theories should guide the tools that we build. So thinking about sense-making theories, information foraging theories, revisiting that now in the age of LLMs. Do those need to update? And from that, can we then build better tools around them? And then more broadly in the long term, I think AI is really changing knowledge work. And through DocETL, I've had a first-class seat to watch hard human AI problems emerge, things like evaluation. I'm now interested in vibe coding. I'm also interested in how organizations are changing with respect to AI capabilities being introduced. So I want to study these problems, do research on them, and teach people. Like I feel like I did for the AI evaluation problem, I want to repeat that. And I'm excited to continue collaborating with folks outside of computer science, my users, to run these studies. So in summary, today, I talked about unstructured data processing, revisiting that now with the advent of large language models. I talked about these 2 loops of data processing. In the inner loop, a key insight being that we can semantically rewrite queries to get better cost and accuracy. In the outer loop, these 3 gulfs of user-facing challenges that we should design solutions for. And what's next? I think we are only at the cusp of unstructured data processing. I think there's lots of exciting challenges deep in the stack, broad in the lifecycle, and for building the next generation of systems for knowledge work. Thanks to my awesome collaborators, I had such a great time in my PhD working with them. And with that, I'm happy to take any questions.
Great. Glad we have time for questions. I'd love to start. I was really interested in what you were saying about speed breaks and users rushing through, and became curious that if you were to add points of friction or more engagement to keep users in the loop, where it might be most beneficial to do so, whether that is getting them to read more of the source documents or finding alternative representations that have a kind of equivalent goal, or is it just getting more labels in terms of helping safeguard correctness, or something else entirely? What do you think?
That's a fantastic question. So I think a big reason, I want people to read data as much as possible. That's my ultimate goal. But I think what makes it very difficult in a system like DocWrangler is that the data is too big and most of it is not relevant, or the relevant parts are too sparse in the document. So I'm interested in ideas for, okay, how can we quickly find those, visualize those in better ways, either within the document or across documents. Getting users to look at data in any which way, in ways that we feel confident, like actually reflect that source data, I think is the #1 thing that I want to do for these speed breaks.
Have you seen any failure cases that have resulted from people not doing that, and that they think that they're getting an analysis result that is responsive to their question, but it's not because there was the insufficient attention or understanding of the data and associated validation?
I think it's a good question. It's very difficult to answer that. I can tell you what I've noticed is that people don't know what's in their prompts at all, because DocWrangler is writing them, and they've not provided any feedback. And in turn, what happens is their operations are extracting more things or enriching the summaries in ways they didn't expect. They read 3 or 4 of them, and they feel like, OK, it's good. Let me just send it or ship it to some downstream. A lot of people like to also do visualization on some of these structured outputs. And I feel like that is a little bit concerning. Whether or not they ever find out that they've made a mistake is another question. But the fact that the operations clearly make assumptions that the user has not specified in any information is very concerning. Yeah. Yeah.
So I have a question about, I think both like the prompt might be wrong, or whatever is written might not perfectly capture, but like the response to whatever thing, if that is also provided by an LLM, might not be perfectly matching what was in the prompt, or are the like low-level operations being done by like database primitives?
Oh, good question. They're all LLM-powered algorithms to some extent. So something like reduce, you have like thousands of documents, and you have LLMs doing something, and then maybe a deterministic, memory that's kept. But
so one hypothesis I have would be one way to introduce a speed break that would presumably show something very useful is like forcing people to say, yes, these things that my LLM says are matches, you like them.
Yeah.
Here are some I'm less sure about. Tell me which ones are or are not, and maybe rank them and force them to like give feedback on K out of each percentile. Like that seems like something, given that the LLMs, who knows how good they are at knowing how confident they are, they actually match to a given query.
I love this idea, and I also think it speaks to the broader point that we can develop custom interactions and ways of specifying each different operator. Like filters are a very different operator to even provide this specification for than something like an open-ended map. We went out with like these relational variants of the natural language, but I think there's a lot more we can do to improve the interface.
But especially given that you have like LLMs all the way down.
Yeah. Yeah. Yes.
So in DocETL, you're dealing with unstructured data by essentially in a very explicit way, right? So if you rewrite directives, etc. Another way to deal with unstructured data is rely on the underlying sparsity in the data and just employ various techniques like pruning, etc. Still extract a lot of information and then reduce costs.
Yeah.
Did you explicitly compare these two approaches? Like, how do they fare against one another?
It's a great question. So we actually have pruning-based rewrite rules or rewrite directives in our framework. I didn't talk about them, but we have pruning rules based on like semantic similarity of embeddings, like top K chunks, pruning rules based on code to drop or parts of documents or regular expressions. So all of these are searched for in the search algorithm. Yeah. Yes.
So you mentioned that users make many iterations. Seems like there would be an opportunity to study those iterations to sort of learn patterns of, so you could just jump to the right end result, or at least identify places where, maybe you should double click on this thing, right? Because many other people have found that necessary for trust is ambiguous, et cetera.
Yeah, totally. I mean, we haven't explicitly studied it. I want to now that we have much more data. But I agree with you there. Yes, Leilani. Oh, sorry.
So something interesting that you mentioned in the talk is that there's like a lot of this rich information in all these documents, and people don't know what's in these documents. Mm-hmm. So they could go on a little bit of a fishing expedition and kind of pick out what they want to learn and not realize they're kind of exploring in a biased way. And I'm just curious, have you thought about tackling that problem in the future?
It's future work. I would love to.
Yeah.
Yeah. I think the way that people do it now, right, is they like write these exploratory open-ended operators and they want to like consume those results. But there's a lot of, decision making or agency given to the LLM and trying to find what is interesting, and that part is very concerning to me. Yeah. Many people had questions.
Time for one or two more.
Okay. I know Dan had a question. We can.
Yes. So I was interested in task Exodus. Sorry,
which is-
task what?
Sorry, task cascades.
Task cascades, yes. Task cascades.
Yeah, that's
Very few people will get this joke, but yeah.
Yeah, so that is really the database angle, which doesn't exist, as far as I know, in React or Codact or recursive language models, the new trends in LLMs. My understanding, this is something that exists in databases. That's what we can do, bring to the table. But how does the optimizer really work in this case, in which you only have this vague semantic equivalence between the different query plans? And I understand you're using users, you're using real humans to check which one is better. So does this mean that you can only consider as many alternative plans as the users are willing to label? Or are you able to explore many more plans once you have a few labels for some of these plans?
Good question. So the labels are given on like original one plan or so, and there's an accuracy function that people compute. And often this is thing like check if this location was actually present in this data and then try to maximize the recall. So that kind of function can be computed independently of specific labels on individual plans. And then going to your task cascades question, that setting users don't provide any labels because the goal is to rewrite queries to be cheaper but maintain the same accuracy with respect to some Oracle implementation. So we can have that Oracle, like GPT-4o, label thousands of samples. And then we can go explore lots of different alternative operations to try to find that cascade with some accuracy target. And yes, I think you have a good point that if your LLM agent is not good, you don't get great operations that you can put in the cascade. But fortunately, these agents are really awesome, and they're good at understanding the task. And so I think we should use them. Yeah, great question.
One more question.
Sure.
Yeah, so thanks for the talk, by the way. So I was just wondering, in the first work on the DocETL, you mentioned that like LLM agents are going to go off and do this, I think the query rewriting part.
Yeah.
I might have missed this part, but you mentioned like the cost like reduced over like the total pipeline, but what is the cost of those rewrites, and like did you look into maybe what kinds of models you need for these rewrites, and how much do they like cost per time that you run this whole pipeline?
Yeah, it's a great question. You should check out the paper on our latest version of the optimizer. A lot of all those costs are reported there. That's the easiest way to answer. But yes, at scale, things really get cheaper. Yeah.
Thanks, everyone. Let's thank our speakers.